we are in the first part of differential linear momentum balance equation. We have discussed few chemical engineering applications of differential total mass and linear momentum balance equations. Now, we will derive the left hand side of the differential linear momentum balance equation. We will understand why we do only the left hand side as we go along. Okay. So, as we derived the differential mass balance, for the differential momentum balance we start with the integral balance equation. So, we start with the integral linear momentum balance equation. We, because the vectorial equation, we write only the component of that, x component of the integral linear momentum balance equation. So, we will also derive throughout only the x component of differential momentum balance equation. Now, we will consider a small control volume as shown here, and this small control volume is inside a pipe of a rectangular cross section. As explained earlier, we take a rectangular cross section so that we can work in Cartesian coordinate system. Now, we consider a fixed control volume. So, we can bring in the time derivative inside the integral sign, and when we bring inside, rho v x can be function of both space and time. So, it becomes a partial derivative. When you integrate, all the spatial variations are taken into account. So, only time variation remains, so it is d by dt. In this case, because it is inside the integral, rho and v x can be functions of time, hence a partial derivative. Of course, these terms are remaining the same. Okay. So, this tells about the rate of change of x momentum within the control volume, net rate at which x momentum leaves through the control surface, and sum of forces acting on the control volume. Now, the control volume is shown here, and the coordinate axes are same x, y and z, and it's a cuboidal control volume of length delta x and then delta y and then delta z. Okay. Now, let us simplify the different terms in the integral balance equation. When I say simplify, we are going to apply this integral balance equation for this small control volume, and the way in which you should imagine is that this control volume is inside our equipment, a small region inside our equipment, and then as we run for mass balance we will shrink it to a point. Now, let us take the rate of change of x momentum term. We will take an average density and x velocity in this region, in this small control volume, and because it is average, it is just a constant. So, I take the time derivative out of the integral, and what is left out is integral dV, which is the volume of this control volume. Being a cuboid, this volume is delta x, delta y, delta z. Okay. Right now, these represent average values. When we take limit and make it as a point, they become point values that we have already seen under mass balance. So, it is very important to understand the derivation for the differential mass balance, so that you can easily extend to differential momentum balance later on, in fact any balance as well. Okay. Okay. Now, of course, this term represents the rate of accumulation of momentum in the control volume. Now, let us move on to the net rate at which x momentum leaves the control surface, which is a convective momentum. So, this represents net rate of flow of x momentum out. Out is important because n is outward normal through the control surface by convection. Okay. Now, there are 6 phases to the for this control volume, cuboidal control volume. If you express this convective momentum for the 6 phases. This is how we represent, as we are seeing here. Now, what are the 6 phases? The left hand side phase and the right hand side phase, okay. And then we have the bottom phase and the top phase, and then we have the rear phase and the front phase. And then now you have inflow through the left phase, okay. You have inflow through the bottom phase, you have inflow through the rear phase, and then the other 3 phases there is outflow, which is the right phase, the top phase and the front phase. Now, how do we write this rho Vx V dot n dA? Okay. We have written this as rho I Vi Ai Vx. Let us understand that. In writing this, we have made 2 assumptions. It is not assumption, it is valid for this case. What is that? The velocity is perpendicular to the phase. That is why this V dot n has been just written as Vi. And then we also taken this rho Vx V dot n to be constant. So, I have left with integral dA, that is why I have Ai here. Okay. Other than that, this rho is written here and this Vx has been written here. I want to emphasize that the first, this represents rho and this Vi represents V dot n, V vector dot n vector, and of course integral of dA is represented as this Ai, and this Vx and this Vx are same. The reason for emphasizing this is that whenever we write a momentum balance in a particular direction, in this case x direction, that component of velocity appears on the rightmost. So, that looking at the, here you have 2 velocities, what is that? We have Vi and then we have Vx. This Vi depends on the phase for which we are writing. That Vi could be Vx if you are considering the phases along x direction, it could be Vy if you are considering phases along y direction, Vz phases along z direction. So, rho I Vi into Ai account for the mass flow in a particular direction, entering and leaving, in this case of course leaving, okay. And this Vx accounts for the direction of momentum, okay. That is why I am very specific that first is rho, Vi represents V dot n for a particular direction I, and then Ai represents the area of that particular phase, and we are writing x component momentum balance x direction, and hence this Vx is the velocity in the x direction. Until rho I Vi Ai we have mass flow in a particular direction. Moment you multiply with Vx, you get x momentum, okay, flow of x momentum in a particular direction. So, we have similarly we write for inflow phases and we take care of the negative sign, because we are expressing V dot n in terms of Vi, we take care of the negative sign ourselves, okay. Okay. So, now let us consider the phases pairwise. Okay, now, considering the phases along the x direction, I am going to consider the left hand side phase and the right hand side phase. Rate of flow of x momentum entering at x is equal to rho Vx Vx delta by delta z. Okay, let us understand this. Many terms are familiar here based on mass balance. What are the terms that are familiar? Rho Vx delta by delta z is very familiar to us. The left hand side Vx, I am very specific, the left hand side Vx. Okay. So, rho Vx delta by delta z is familiar. What is the meaning of that? As we have seen earlier, 2 ways of interpreting. This is the velocity multiplied by area gives volumetric flow rate, multiplied by density gives the mass flow rate. Other way of interpreting, Vx is the volumetric flux, multiplied by density gives mass flux, multiply area gives you mass flow rate. So, that is the significance of that term. We are interested in the x momentum, so multiply with Vx. Okay. So, rho, if you want to write this, rho Vx as per our earlier nomenclature, earlier we said rho I and then Vi and then Ai and then we said Vx. If you want to write this along the same way, then rho Vx, area is delta y delta z, and then we have Vx. Now, the density and velocity can change its spatial location, that is why, and we are evaluating the rate of flow of x momentum entering at this phase, and this phase is at x, and that is why we evaluate at x. Okay. So, if you understand this clearly, all other terms become very simple. Okay. Now, let us write it for the x momentum leaving at x plus delta x, same expression, but evaluated at x plus delta x. Okay. So, the inflow rate of x momentum entering is shown here, rate of x momentum leaving is shown here. Okay. Rho Vx and then Vx evaluated at x, and then rho Vx evaluated at x plus delta x multiplied by the area. Just to repeat, area of this phase is, this is delta z, this is delta y. So, area is delta y into delta z. Okay. Once you are done for x direction, we will analogously do for the y direction, but in this case I like to repeat for y and z directions to understand that better. Okay. Remember, once again it is rate of flow of x momentum, but now because of mass flow entering and leaving along y direction, that is why we have rho Vy into delta z delta x, which represents mass flow which enters at y, and because we are considering flow of x momentum, we still multiply by Vx. Okay. So, please pay attention that always the second velocity represents the velocity component along the direction in which we are writing the momentum balance. Okay. Now, let us write the rate of flow of x momentum leaving at y plus delta y, same term as that. Once again want to emphasize that it is rho Vy Vx all evaluated y plus delta y. What is the area now? The area is delta x into delta z. Okay, that is the area, and let us do that for the z direction as well. So, rate of flow of x momentum entering at z, okay, is rho Vz. So, rho Vz delta x delta y, the area is delta x and then delta y, that represents the mass flow along the z direction, because interest in x momentum multiplied by Vx. Now, the velocities can vary with space, that is why evaluated at z. Similarly, rate of flow of x momentum leaving at z plus delta z, rho Vz Vx evaluated at z plus delta z. So, now if you look at this, let us focus on the flows shown in this diagram. If you look at the second velocity component is always Vx, look at here Vx, 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 Vx and Vx. So, if you look at the diagram itself, we should be able to tell that we are writing the x linear momentum balance along the x direction. Look at the first component Vx, we have rho Vx, of course, if it along take with delta y delta z, that tells about mass flow in the x direction entering and leaving. Similarly, mass flow in the y direction entering and leaving, mass flow in the z direction entering and leaving. So, the way in which you write should go along with the physical interpretation. Now, if you look at this, it has a close analogy with what we have written for mass balance, differential mass balance. Okay. Now, if you look almost same, only difference is the presence of Vx in all the terms. Okay. This is the left hand side is the control volume shown with all the inflow outflow mass flows, right hand side is a diagram with all the inflow and outflow of x momentum. What is the difference? For example, you have rho Vx here, you have rho Vx into Vx here. If you take for example this flow, we have rho Vy, I have rho Vy into Vx. In fact, that is how I generated this figure also, copied this, pasted here and edited all by adding a Vx. Okay. So, that shows that if you multiply with the Vx, you get the x component of velocity. Suppose if you are writing y component etc., you will multiply by Vy all the terms. Okay. So far this momentum term is not something new to you, mass into velocity is something very well known to you, but only difference is you would have so far written in a physics class etc. for a solid object. So mass was known, mass of the solid object into V vector. So there was no discussion about the mass at all, mass is given, V could be any direction, it could be along x direction, y direction, z direction, but now this mass represents mass of a fluid, and hence that mass flow can happen in x direction, y direction, z direction. That is why we are focusing on the giving importance to mass also, the direction and the component of velocity also. That is why we have rho and then let us say V I in general, and then here we have V x. Okay. This was just written as, of course, multiplied by area etc. area, all this put together was written as just m, and here you had V vector. That V vector we are taking one component as V x, so you would have written as m V x. No further discussion would have been required for just a solid object, because it is a fluid flow which can take place in 3 directions. We also discuss the direction of the mass flow as well. Now let us put them all together in the integral linear momentum balance equation, both for the time rate of change term and the net convection term. The first term we have seen as dou by dou t of rho V x and then the volume. Second term, the net rate of flow of x momentum, net rate of flow of x momentum along the x direction. Remember, it is net outflow, that is why it is out minus in, whatever is leaving minus entering, okay. And that is along x direction. These two represent along y direction, out minus in. Similarly, these two terms represent out minus in. Remember, all represent rate of flow of x momentum. What the mass flow associated with different directions carries with them the x momentum. So these two represent mass flow leaving and entering along x direction, these two for y direction, and these two terms for z direction, and right hand side we have sum of forces acting on the control volume. Now as we have done for the differential mass balance, we will divide by delta x, delta y, delta z, the left hand side alone. Okay. We said in the outline that we are going to derive the left hand side alone. Okay. So we will divide it by delta x, delta y, delta z. So now the significance in the earlier terms were they were representing for example, if you take these two terms, they represent net rate of flow of momentum leaving along x direction. Now this term represents same significance per unit volume, okay. So if you significance of that is that these two terms put together is that net rate of flow of x momentum leaving through the control surface per unit volume. Now we will shrink the control volume. We had discussed this when we derived the differential form of mass balance. We will shrink the control volume to a point. Objective is that we need a equation which is valid at every point in the flow domain, so that when you solve, see, remember we are going to solve this and finally get the velocity profile. I need velocity profile along the entire section, every region. So I need an equation which is valid at every point in the domain, and hence shrink the control volume to a point. Also we said that the geometry should be maintained same, should remain as a cuboid. So every length along every direction also goes to 0, and what happens now, all these were average values, these were average values within the region, they become point values. These were average values in the face, they also become point values, and hence you get a differential equation where now all the variables represent point values, okay. And of course this derivative as limit delta x tends to 0 becomes a partial derivative dou by dou x of rho Vx Vx. Similarly, in the y direction, similarly in the z direction. As I have told you earlier, to understand, you can understand the term in one direction and analogously extend to other directions, but with a caution to take care of the correct velocity component. When you extend other direction, make sure, for example, if you understand the first two terms, it has rho Vx Vx. When you extend other direction, you should understand which velocity is to be replaced with Vy. It is this velocity, the left hand side velocity, which is to be replaced with Vy. You may be wondering why so particular about this direction. It has a implication later on as well. After we discuss surface forces, you will understand that. Right now, we will stick on to that. Also becomes easy. Look at the differential equation left hand side. All the second velocity components are Vx. Tells you that it is a momentum balance along the x direction. Now, let us compare with the continuity equation or the differential mass balance and see what are the difference. As we expect based on the derivation etc. Based on the derivation, all these terms are multiplied by Vx, of course not outside, that can also vary. So, you multiply here with the Vx, with the Vx here, with the Vx here. So, in fact, if you are very clear with about the differential mass balance, you can write the x component of linear momentum balance very easily, just multiplying everywhere with Vx, of course including the accumulation term as well. Now, we also look at predominantly we looked at the left hand side, we also look at the right hand side forces. We had two forces, the body force and surface force. We are going to look at the body force only now. Okay. You will see the reason shortly. Okay. The sum of forces in the control volume has two components split into body and surface forces. Okay. Now, the body force is gravitational force, as I told you that is the only body force which we are going to consider. Now, so far in the earlier examples, we had a well defined control volume, and so gravity was always acting along one axis, it could be z axis, y axis etc. But I can have a geometry along aligned any particular angle. Okay. For example, one example is shown here. What is a control volume aligned along a general coordinate axis shown here, it need not be aligned along our usual x y z axis. Okay. Now, what is the application? For example, you have inclined plate which is shown here, and then let us say water flows along that. In this case, it will be convenient for me to take a coordinate axis which is aligned along the flow direction. I will take x like this, y like this, z like this, which means that this is not your gravity always acts along the vertically downwards, but now your coordinate axis is not aligned along your usual x and y z axis, which means that you can have components of gravity along your chosen x y z axis. Your gravity acts vertically downwards. If your coordinate axis also has one axis along that vertical direction, then there will be only one component of gravity, let us say g y or g z. But suppose your coordinate axis is not is more general, which is not aligned, where the vertical axis are not aligned along the gravity, then you can have components of gravity along your chosen x y z axis, okay, which are not your regular x y z axis. That is why in general we represent G as gxi, gy j, gzk. In earlier examples we had only one of them, either gy or gz. Okay. So, make it more generic, we represent this way. Okay. So, now we will remember the body force is a volumetric force, or it is expressed as per unit mass or unit volume. G is the gravitational force per unit mass. So, we multiply by the mass of this control volume. What is that mass? It is density into the volume of control volume, that gives a mass there. At this point it is an average value, rho is average, of course G is just a constant. As we have done for the left hand side, we also divide by the volume delta x, delta y, delta z, shrink to the shrink the control volume to a point, and now what you get is rho g. What is the difference between this term and this term? This is rho g into delta x delta y delta z, and you are dividing and then you are taking limit. So, now this rho becomes a point value as we have done earlier. Earlier this is the average of rho in this control volume. When you divide and shrink it to a point, so now this represents the body force because of the gravitational field, the gravitational force per unit volume. Once again remember, this is gravitational force per unit volume. This expression is gravitational force or body force. Here when we are divided, represents the body force or gravitational force per unit volume. Of course, once we pool all the terms, we look at the significance of each term there, but as we go along also we should be familiar that all the terms are per unit volume basis. Okay. Surface forces are all the more involved, and hence we pay special emphasis to that. To understand the surface forces acting on the faces of control volume, we take a diversion. Okay. We take a diversion where to solid mechanics. Okay. Why should we take a diversion? Okay. First of all, if you are on a highway travelling at let us say 100 km/h and you look at diversion board, what is the first response? Irritation. You get highly irritated that you take a diversion. But if on the diversion, let us say you are going to meet fluid mechanics, and if on the diversion you meet solid mechanics, and that solid mechanics tells that I know fluid mechanics very well, good friend of mine, we share a lot of commonalities, then you are happy. Exactly the same situation now. Many of you may be wondering why take a diversion solid mechanics, you may be perplexed also, but based on feedback from students that question has been there, but as we go back and forth to solid and fluid mechanics, they were very much satisfied about the progress of taking a diversion. Okay. And other reason for going to solid mechanics is that easier to understand about surface forces when you discuss through solid mechanics. And of course, other advantage is that we can see the parallel between solid mechanics and fluid mechanics. We said that is one of the objectives of the course as well, that we discuss the commonalities between solid and fluid mechanics, of course justifying the term continuum mechanics. Okay. So, one is look at the generalities between them, second is easier to understand the surface forces when it discussed through solid mechanics. Okay. Very colorful slide. After several lectures, as I told you, we will derive the differential form of the linear momentum balance named as the Navier-Stokes equation. The authors who derived that, Navier and Stokes, and this slide shows the various steps involved in the derivation, which I fondly call as the journey to the Navier-Stokes equation. We are somewhere in the beginning. I will not discuss the entire slide now, you may not understand that. Let me go to a point where we are now. Okay. Some of the steps should be familiar to you. We started the Newton's second law of motion for the system. We applied the Reynolds transport theorem and then derived the integral form of linear momentum balance. LMB stands for linear momentum balance. Now, we use the integral linear momentum balance for a small control volume, that is what we have discussed in the last few slides, and then derived the differential form of linear momentum balance, not the complete form. What we have derived is the left hand side, okay, which was almost similar to our mass balance, that is why we could derive that, and then we consider only the body force on the right hand side, which is the gravity on the right hand side, that is where we stand. Just to understand the surface forces, we take a diversion. This one represents the first time we visit a solid and come back to fluid mechanics. Okay. So, first time we take a diversion to solid mechanics, you will understand what are the boxes here, what do they represent later. So, just to show that we take a diversion to solid mechanics to understand about surface forces, okay, and then rest I will explain later. This 2 and 3 represents second time, third time when you go and come back to solid and fluid mechanics, I mean shuttle between solid and fluid mechanics. Okay, that is a summary of what we have done so far under differential linear momentum balance. we started with the integral momentum balance applied for a small control volume, derived the differential form of linear momentum balance equation. We have derived the left hand side, which has the rate of change of with respect to time term and then the convective momentum term. And we are on the right hand side, we have looked only at the body force. We are yet to look at the surface force on the right hand side. To understand that, we are taking a diversion to solid mechanics. That is where we stand.